A very good morning to one and all. My name is Dr. Vishalli, and I am working as an assistant professor in the Department of B.Sc Computer Science at IIMT College of Science and Technology, Greater Noida. The topic of today's presentation is semiconductor materials. So let us begin with this session. First of all, the contents or brief layout of this presentation. So in this session, we will be discussing the classification of solid materials, energy bands in the solid, classification of the conductors, insulators, and semiconductors on the basis of the energy bands, and lastly, the classification of the semiconductor, that is intrinsic and extrinsic semiconductors. First of all, the classification of the solids or the classification of the solid material. So on the basis of their conductivity, we can divide the solids into three categories. First categories are conductors, insulator, the second one, and third one are the semiconductor materials. So what are conductors? So as the name suggests, conductors are the good conductors of the electricity. They are characterized by the large electrical conductivity and a very small electrical resistivity. The large value of the electrical conductivity in the case of the conductor, it is due to the presence of the mobile charges or the presence of the large number of the free electrons. So due to those free electrons are able to carry the electric current. So in conductors, we have large number of free electrons. That is why they are good. They are called as a good conductor. They are able to conduct the electricity through them. So the examples of the conducting material, all the metals basically, such as silver, copper, aluminium, etc. The second category is insulating material, insulators. So insulator materials are the materials which are characterized by the poor electrical conductivity. They are the bad conductors of the electricity. Now, again, the reason for the such property of the insulating material is that they don't have free electrons, which are required to carry the electric current. The examples of insulators are such as glass, quartz, rubber, etc. The third category is semiconductor materials or semiconductor. Now this category, it lies between conductors and insulators. They have the poor conductivity as compared to the conductors, but their conductivity is higher than that of the insulators. And when the temperature of the semiconductor is increased, their conductivity increases, or we can say that the electrical resistivity of the semiconductor decreases with increase in temperature. That is why we also call that they have the negative temperature coefficient of resistance, because resistivity decreases with increase in the temperature in the case of the semiconductor. So they lies between a conductor and insulator. And one important property of semiconductor material is that their resistance can be controlled by controlling various factors, such as one of such factors is temperature. So if we are able to control the temperature, we can basically control the electrical conductivity in the semiconductor. So this is one of the important property, that the resistance depend upon the different factors which can be easily controlled. The examples of the semiconductor material which we will be considering in this presentation, that will be silicon and germanium. So these two are the examples of the semiconducting material. Now, in order to understand the semiconducting materials, we first need to understand the formation of the energy bands in solids. Now, according to the modern physics, in an isolated atom, as we all know that in an atom, we have a nucleus in which protons and neutrons are there. And outside the nucleus, we have the orbits on which electrons are revolving. So in an isolated atom can revolve only on those permitted orbits and not in any intermediate orbit. I have considered here examples of silicon and germanium. Silicon has atomic number 14. So we can see clearly that it has 14 electrons outside the nucleus, and the 4 electrons, they are in the outermost orbit. These are called as a valence shell electron. Similar is the case in the case of the germanium. The atomic number is 32. And it also has a 4 valence electrons. So from this diagram, it is clear that electrons are revolving in certain orbits, and certain amount of energy, a fixed amount of the energy is associated with each orbit, and electrons are moving in a particular orbit possess that amount of the energy. Now, what happens in solids or in crystals? Now, as we all know, in crystals or in solid, we have the closely packed arrangement of the atom, meaning the atoms are lying adjacent to each other. They are very close to each other. So, in crystals, individual atoms are closely packed. So, that is why the resulting energy levels of the atom, they will get modified because of the interaction between the atoms. So, as the atoms are lying very close to each other, there will be interaction between them. For example, the valence shell electron, it is under the influence of the nucleus, of its own nucleus, and also it is interacting with the atoms, and it is under the influence of the other nucleus as well. So that's why their energy levels, they will get modified. Now, what happens is that the coupling between the electrons of the atoms results in the band of the closely spaced energy level instead of the widely separated energy level. Just like in isolated atom, as we say that we have a definite energy level in which electrons are revolving. But as those atoms will come closer, their outermost energy levels particularly, they will get modified. And how they will be modified? Rather than all the electrons in a single energy level, now we have a group of energy levels which are slightly different in the energy, and that group is basically called as a energy band. So that is how the bands are formed in the solids rather than a definite or a single energy level which is there in an isolated atom. So that is why, because of that closely packed arrangement in the solids, rather than a single energy level, we will be getting the energy bands. So the closely packed energy level, which slightly differ in the energy, they will form the energy band. So that is how the energy bands are formed in the solids. Now we will talk about the valence band, conduction band, and forbidden energy gap. Now, valence band, we all know the valence electron. What are valence electron? The electron in the outermost shell of the electron. So all those valence electron from large number of the atom, they will form a band that will be called as a valence band, the valence energy band. So the energy band which possesses the valence electron, that will be called as a valence band. It is comparatively lower as compared to the conduction band. It is completely filled up. The band which is lying above the valence band, that will be called as the conduction band, and it is normally empty at 0 Kelvin. And conduction band basically contains a free electron. Electrons from the valence band can jump to the conduction band, and then they will become free. There are large number of empty energy levels in the conduction band. So electron can go from valence band to the conduction band, then it will become free, and those free electrons are contributing further to the electrical conductivity. Third is forbidden energy gap. Now, the gap between these two bands, the gap between the valence and the conduction band, that will be called as the forbidden energy gap. And as we are imagining it along the energy, so it is associated with some definite amount of energy. This energy is denoted by Eg. So Eg is the amount of energy basically that should be given to an electron so that it can go from the, it can jump from the valence band to the conduction band. So this will be more clear in this diagram, as I have said earlier, that we have valence band. It contains the closely spaced energy level, which are slightly different in the energy of the valence shell electron. So this is a valence band. This is a conduction band, and the gap between these two bands, that is called as a forbidden energy gap. So this is called as a forbidden name because no energy levels are allowed within this region. So that is why it is called as a forbidden energy gap. So in conduction band, we have this is a valence band, and electron can overcome this forbidden energy gap and go to the conduction band. Once the electron will go to the conduction band, it will become the free electron, and larger the number of free electron, larger will be the conductivity of that particular material. So this forbidden energy gap, it varies from material to material. It may be very small, it may be large, or in some cases, as in metal, it is non-existent. Its value will be 0. That there will be no forbidden energy gap, meaning there is no gap between valence and the conduction band. So on the basis of this energy level diagram, or on the terms of this valence and conduction band, we can basically distinguish our conductors, insulators, and semiconductor on the basis of this forbidden energy gap. So let's see how can we distinguish the conductors, insulators, and semiconductors in terms of the valence and conduction band. So classification of the conductor, insulator and semiconductor on the basis of the energy band. So in this diagram, first of all, we will consider this first one. It is the insulators. So we can see in insulator, we have valence band, conduction band. Valence band is on the lower side of the energy, conduction band is on the higher side. And there is a gap, that is forbidden energy gap between them. We can see clearly that the energy which is required for the electron of the valence band to go to the conduction band in the case of the insulator, that must be equal to or greater than the 5 electron volt. So this 5 electron volt is a large amount of energy, and at room temperature it is not possible for the electron which is residing in the valence band to overcome this energy gap and move to the conduction band. So that is why there are no free electrons in the insulators, and insulators are bad conductors, are said to be bad conductors of the electricity. Now the question is that is it possible that we will somehow increase the temperature, and by gaining that energy, the electron can jump from the valence to the conduction band? Now, since this gap is very large, so we have to increase the temperature up to a very high range. So at if we are increasing the temperature, it will reach at such a range that it will it will lead to the breakdown of the insulator if we are increasing the temperature above a certain range. So that is why that will lead to the breakdown of the insulator. So that is the case of the insulator. The bottom line is that in insulator, basically electron is unable to overcome the forbidden energy gap to reach the conduction band. That's why these are not good conductors of electricity. Now, third, I'll move to this third diagram. This is about the metals or conductors. So we can see clearly that in the case of the conductors or in metals, the gap between the valence and conduction band is zero. We have here the large number of closely spaced energy levels, and we have electrons in them. And conduction band, we have large number of energy level with no electrons. So the electron from the valence band, it can easily go to the conduction band because there is no energy gap between the valence and the conduction band. So that is why it is easy for the electron to become the free electron, and larger the number of the free electron, larger will be the conductivity. So that is why the metals are very good conductors of the electricity. Now, thirdly, talking about the semiconductor, which is the category lying between the insulators and conductors on metals. So we can see clearly that there is a gap between the valence and conduction band in the case of the semiconductor, which is, in semiconductors, this gap was very large. In insulators, this gap was almost zero. Here is a gap, and this energy which is required for the valence shell electron, valence band electron to go from the valence to the conduction band, it is 1 electron volt. So 1 electron volt energy must be there for the electron to go from this lower to the upper band. So at the absolute zero, at 0 Kelvin, the electron will reside in the valence band. It will be unable to go to the conduction band because it doesn't have the sufficient amount of energy. But as we increase the energy, as we move to the room temperature, then this value of energy is comparatively, or you can see that it is very low as compared to the energy which is required in the case of the insulator. So it is very easy for the electron in the valence band to go from this valence to the conduction band at room temperature. So that is why, as I have told earlier also, that this is temperature control. The conductivity is temperature control. So once the electron will reach the conduction band by overcoming this forbidden energy gap, it will become free electron. Once the electron is free, it will be contributing to the conductivity. It will be contributing to the conduction. So that is why these are called as semiconductors, and they will be conducting as the temperature is reaching the room temperature. And this gap, as we are talking about the semiconductors, this gap for silicon is 1.12 electron volt, and for germanium, this gap is 0.72 electron volt. Now we'll move to the semiconductors. So we have studied what are the semiconductor and how we can define them on the basis of their energy band diagram. So now let's study further that what are the types of the semiconductors. So semiconductors can basically be divided into two types. One are called as an intrinsic semiconductor, and second one are the extrinsic semiconductors. Extrinsic semiconductors are further divided into two categories. One is called as a N-type semiconductor, and second is a B-type semiconductor. So let's study them one by one. First is intrinsic semiconductor. So semiconductor which are extremely a pure form of the semiconductor that are called as a intrinsic. Now what do we understand by the extremely pure form? So extremely pure form means that we have all the atoms which are there in that semiconductor, they all are consisting of that particular material, that is only semiconductor, and the impurity content is very, very less. What is the ratio of that impurity content? That one part impurity is there in the 100 million parts of the semiconductor. For example, in this diagram, you can see we have silicon atom. So we have a large number of silicon atoms are there. So all the atoms are majorly of silicon. If there is an impurity, then it will be like one part of impurity is present in 100 million parts of the semiconductor. So impurity content is very, very less in the case of the intrinsic semiconductor. That is why they are called as an extremely pure form of the semiconductors. Now, again, in this diagram, this is a silicon atom. As I have also shown earlier, that silicon, it has atomic number 14 and it has 4 electron in the valence shell. So it requires a 4 more electron to complete its octet. So what type of bonding is there? That for example, I am considering this silicon atom. It has 4 electron, which is denoted by these 4 green dots. Now this silicon atom, it is forming the covalent bonding, meaning it is sharing the electron with these 4 silicon atoms. So by sharing or by forming the covalent bond, now the octet of this silicon is complete. It has attained the 8 electron, and also the atoms, other silicon atom with which it has formed bond, their octet is also complete. So this type of bonding in which the sharing of the electrons is there, that is called as a covalent bond. So in this structure, in this semiconductor, silicons are bonded in the covalent bond. So each of the 4 silicon atom, they take part in forming the covalent bond with the neighboring atoms, and they will complete their octet. So this is the structure of the silicon lattice. Now, at absolute zero or at 0 Kelvin, all these electrons, they are in the covalent bond, or we can say they are tightly held by their parent atom. These are the parent atom. So at absolute zero, all these valence electron, all these 8 electron, they are tightly held in this covalent bonding by their parent atom. So there are no free electrons. We require free electrons for the conduction. So because at absolute zero, no electron is free electron. All the electron, they are bonded in the covalent bonding and they are tightly held by their parent atom. So that is why intrinsic semiconductors, they are insulators. They behave as an insulator at absolute zero. So at absolute zero, or at very low temperature, since there is no much availability of the free electrons, all the electrons are in the bonded position. That is why they will act as an insulator. Next, we will see what will happen if we increase the temperature. So let's suppose that we have increased the temperature to the room temperature, nearly about 300 Kelvin. So whenever the temperature is increased, then what will happen? Some of the covalent bonds will break. When the covalent bond will break, then the electron will be released from that covalent bond. So we can say that the electron which was earlier in the bonded position, it will become free. So electron will become free. So like this, for example, this electron is becoming free. The electron is becoming free. So it is no more under the influence of its parent atom. And in the place of the electron, we will have a vacant space will be generated. So that vacant space, that is called as a hole. So we can say that whenever we increase the temperature, there is a generation of a free electron hole pair. Whenever electron is getting free, one hole is created, the vacancy of the electron or the absence of the electron, that is called as a hole. So there is a generation with the increase in the temperature, there is a generation of the free electron hole pair, right? So the electron become free and the vacancy is created in the broken covalent bond. This vacancy is called as a hole. Now, what is hole? It is not to be confused with that it is some kind of particle. It has no its own existence is not there. So it is just the vacancy which is generated because the electron has left that place, or simply we can say that it is the absence of the electron in the shell where it could exist, where the electron should be there. Now the electron is not there. That is why it is called as there is a vacancy, and that vacancy is called as a hole. Now, these free electrons in hole, as I have told earlier also, they are always generated in pair. When once the electron will leave the place, only in that the hole will be generated. So electron holes, free electrons and holes, they are always generated in pairs. This type of generation, due to the increase in the temperature, this is called as a thermal generation. Now, one more important thing is that since the crystal remains electrically neutral, so whenever an electron move, a hole will be left behind with the net positive charge equal in magnitude with that of the negative charge of the electron. So this is an important hole. As I have told that this is not a particle; it has no its own existence is not there. But practically, for all the practical purposes, we will view this hole as a positively charged particle, which is having the positive charge equal in magnitude of that of the negative charge of the free electron. So from now on, we will strictly speaking, this is not a particle. It is just the absence of the electron, which is carrying the equal amount of positive charge as that of the negative charge of the free electron. So now we will have two type of particle. One is a free electron. Another it is not a particle in itself, but it is a vacancy which is left by the electron, and that is called as hole. It has equal amount of the positive charge, and free electron, it has the negative charge. So that was the concept of the electron hole. Now let us try to understand that as we have increased the temperature and covalent bond is being broken, then let us try to understand this thing in terms of the energy band diagram. Now, in energy band diagram, the breaking of the covalent bond, which is due to the increase in the temperature, it is equivalent to rising an electron from valence to the conduction band. As the covalent bond is broken, as as a covalent bond is broken, right, the electron has left from its place, then that is equivalent to raising an electron from valence band to the conduction band. The breaking of the covalent bonds mean the electron from the valence band has overcome this forbidden energy gap by acquiring the energy which was there with the increase in the temperature. It will move to the from valence band to the conduction band. So once the electron is in the conduction band, it will become free electron and will contribute to the conductivity. So, and this gap in the case of the germanium is 0.72 electron volt, and for silicon this gap is 1.12 electron volt. The conductivity of the intrinsic semiconductor, it increases with the temperature because the covalent bond is breaking, or we can say that the electron is moving from the valence to the conduction band. So conductivity is basically increasing, or in other words, we can say that the resistivity of the semiconductor is decreasing with the increase in temperature. So that is why we also call that the semiconductors have a negative temperature coefficient of resistance. So that is how we can understand it in terms of the energy band diagram. Next is the possibility of the recombination. As we have seen that the electron and hole pairs are generated with the increase in the temperature inside the intrinsic semiconductors. So there is a possibility that, for example, this electron hole pair, free electron hole pair is generated here, and another free electron hole pair is generated here. So is there any possibility that this electron can fill this vacancy? And this will be called as a electron hole recombination. So this is the process of recombination. So recombination is also there. It is possible for this electron to fill this position, to fill this vacancy, right? And in this process, energy will be released. And that energy which is released, it will be absorbed by some other electron to break the covalent bond or to break away from the valence band, and it will create a new electron hole pair. Right. So this is the process of recombination. So in this process of recombination, the electron hole will disappear as the electron will combine, electron will fill this vacancy. So we can say that after filling this vacancy, there are no free electron and there is no hole. So we can say that free electron and hole, they will disappear. And in this process, energy will be released. That energy will be absorbed by another electron to break away from its covalent bond. It will create a new electron hole pair. So at a given temperature, the rate of generation of free electrons and holes is equal to the rate of recombination. So the possibility of recombination is also there. Now let's see that now we have free electrons generated and we also have the hole generated inside the intrinsic semiconductor. Now let's see the how the conduction is there in the intrinsic semiconductor. So now we have the semiconductor, we have electrons here, we have holes here. So whenever we will apply the voltage across this piece of the intrinsic semiconductor, then what will happen that these free electrons, right, we are talking about the free electrons only, the electrons which are not under the influence of their parent atom. Otherwise, there are large number of free electrons inside the silicon, but all those electrons, they are in the bonded position. They are in the covalent bond. We are talking here only about the free electrons. So what will happen whenever we will apply the voltage across this piece of the intrinsic semiconductors, then what will happen, all the free electrons, they will start to move towards the positive end of the battery, and the holes, as we are saying that we are assuming the hole has equal amount of positive charge as that of the magnitude of the charge on the electron. So the hole, they will, because we are assuming that they are the positively charged particles, so they will start to move towards the negative end of the battery. So there will be the current in the circuit, and the current due to the movement of the free electron, that will be called as a electron current, and the current due to the movement of the holes is called as a hole current, and their direction will be opposite to each other, right? Because electrons current and the hole current, that will be opposite to each other. The holes will move in the direction opposite to that of the electron. So that is how there is a conduction inside the intrinsic semiconductors. Now, moving on, we will talk about the second category, that is a extrinsic semiconductor. Now, the issue with the intrinsic semiconductor is that they have a very small conductivity at room temperature. To enhance the value of that conductivity, we will make use of the extrinsic semiconductor. So, what are extrinsic semiconductor? Extrinsic semiconductors are made by adding a small amount of impurity atom to the intrinsic semiconductor itself. Right. So in intrinsic semiconductor, we will add a small amount of the impurity, then its conductivity can be improved at the room temperature. And this process of adding the impurity to a intrinsic semiconductor or to a pure semiconductor, that is called as a doping. So how the doping is done, in what ratio the impurity atom should be there, let's see that. So doping is done at a rate that there should be only one impurity atom should be added for 10 to the power 6 to 10 to the power 10 semiconductor atom. So if we have 10 to the power 6 to 10 to the power 10 semiconductor atom, then in that atom, within that atom, there could be one impurity atom, and it is added at the time of the growth of the crystals. So this is a ratio, and doping should be must be done in this ratio, that one impurity atom should be there for 10 to the power 6 to 10 to the power 10 semiconductor atom. So on the basis of the impurities which are added, they can be divided into the two types. One is a donor type impurity and another is called as a acceptor type impurity. So let us see what is donor type impurity. So donor impurity, that is also called as a pentavalent impurity. So as a name suggests, pentavalent meaning penta plus valent, meaning the atoms which have the penta 5 valence electron. If there is some atom which is having the 5 valence electron, then that will be called as a dopant impurity, or sorry, that will be called as a donor impurity. So when the dopant is a pentavalent atom that is containing the 5 valence electron, then that will be called as a donor impurity, and this doping will be called as a donor doping. So the semiconductor which are formed as a result of this by the addition of this pentavalent impurity, that semiconductor is called as a N-type semiconductor. And the impurity, the example of the donor impurities are arsenic, phosphorus, antimony. Basically, these are the elements of the fifth group of the periodic table. So that is the donor impurity, which is also called as a pentavalent impurity, and it is formed by adding the pentavalent atom to the silicon or the semiconductor lattice. The second impurity is the acceptor impurity. It is also called as a trivalent impurity. Now trivalent, tri plus valent, meaning the when the dopant is trivalent atom, that is an atom, it is consisting of the 3 valence electrons. So this type of impurity, it has a 3 valence electron in its outermost shell. So this type of the impurity is called as a acceptor impurity. The examples of the trivalent impurities are boron, indium, gallium, aluminium, etc. Basically the third group of the periodic table in which we have the 3 valence electron. So two type of impurities, donor and acceptor. Donor type impurity, if we are adding a pentavalent atom to the semiconductor, to the intrinsic semiconductor, and if we are and second is the acceptor impurity, if we are adding the trivalent impurity to the semiconductor atoms. Now, on the depending upon the type of the impurity, we have two type of the extrinsic semiconductor. If we are adding pentavalent impurity, then we will get the semiconductor that will be called as an N-type. And if we are adding a trivalent impurity or the acceptor impurity, then the semiconductor which we are getting as a result, that is called as a P-type semiconductor. So now we will discuss the N-type and P-type semiconductors. So first of all, N-type semiconductor. So in this, as we have already discussed, that small amount of the pentavalent impurity is added to the pure semiconductor crystal during the crystal growth. Now, let us assume that we are adding this phosphorus impurity into the silicon lattice. So by adding this phosphorus atom, what will happen? Now, silicon has 4 valence electron, but phosphorus, it is a pentavalent impurity, it has 5 valence electron. So out of those 5 valence electron, 4 electrons, they will form the covalent bond with the 4 adjacent silicon atom, and the 5th electron will be loosely bounded to the parent atom. It is not in, it is unbounded, it is not in the bonded position. So we can say that it is not in the bonding, it is, but it is still attached to the parent atom. So the 5th electron, it is loosely bounded to the parent atom. And the energy which is required to detach, to remove this 5th electron from its parent atom, it is of the order of 0.05 electron volt for silicon and 0.01 electron volt for the germanium. So we can see that the value of energies are very small, and this can be easily achievable at the room temperature. So at room temperature, practically all such atom, they will become free. So in this way, we can say that the phosphorus is contributing one additional electron in the system. So in this way, each impurity atom or each phosphorus atom, it is donating one electron to the conduction band. So that is why this is also called as a donor type impurity. So this will be more clear in this diagram. This was a phosphorus impurity atom which was being added in the semiconductor atom. So it has 5 valence electron. These 4 electrons, they will form the covalent bond with the 4 silicon atom, and this 5th electron, it will be loosely bounded to this phosphorus atom, and a very small amount of energy is required to set this electron free, and that energy is easily achievable at the room temperature. So this electron will become the free electron. So we have other impurity atoms also. So basically, we are getting by adding the donor type of impurities, we are getting the free electrons in the semiconductor. So that is why we can say that the electron, the number of now electrons will be more, the number of free electrons will be large. because we have added the pentavalent impurity. So in n-type semiconductors, the electrons are the majority carriers, and holes which are produced by the thermal generation only, their number will be less. So we can say that in n-type semiconductors, the electrons are the majority carriers and holes, they are the minority carriers. And after donating the electron, now this phosphorus has donated this electron. So after donating this electron, this phosphorus, it will become the positively charged ion. So the net amount of charge on this atom, that will be positive. And this is tightly held because still it is in the other four covalent bonds. So it is tightly held by other four covalent bonds of the crystal. So it is not free to move. That is why it is called as a positively charged immobile ion. The net charge on this atom, that is positive, and it is held by the covalent bond. That is why it is called as a positively charged immobile ion. Now let us try to understand this thing in terms of the energy band diagram. So whenever the donor impurities or pentavalent impurities are added to the intrinsic semiconductor, the energy level, they will get modified. So the modification, it is clearly what modification is there, that is clearly shown in this diagram. So what happens is that allowed energy levels are introduced at a very small distance below the conduction band. So this is called as a donor energy level. So the energy band diagram of the semiconductor, that will get altered, and a new energy level, a donor energy level, that will be there just below the conduction band. And a very small amount of energy is required for the electron in this donor energy band to move from this band to the conduction band. And therefore, at room temperature, almost all the 50 electrons of the donor atom, they are raised to the conduction band, and the conductivity of the material, that will increase considerably. So that is how, by addition of a pentavalent impurity, the conductivity of the semiconductor material, the conductivity of a pure semiconductor material is enhanced. Now next is a conduction in the n-type semiconductor. Now in n-type semiconductor, we have excess number of electrons. We have majority of the electrons, as holes are the minority carrier and electrons are a majority carrier. So this is semiconductor. We have positive immobile ion. They are shown by these positive circles. And these solid dots, the black dots, they are representing the free electron. Because in n-type material, the majority carriers are free electrons. So we have shown only here the free electron. So what will happen whenever we are applying the voltage across the terminals, then all the electron will start to move towards the positive terminal of the battery, and they will constitute the electric current. So this type of conductivity is called as an n-type conductivity. So as electrons, they are more as compared to the hole, the conduction in n-type material is due to the majority carriers electrons. So that is how the conduction is there in the n-type semiconductors. Now moving on, the second category, that is a p-type semiconductor. So in p-type, we are adding a small amount of the trivalent impurity or acceptor impurity. So what happens is that when a trivalent impurity is added, then in trivalent meaning the impurity, it has 3 electrons in the outermost shell. So let us consider that we are considering this impurity, that is indium. So indium, it has 3 electrons in the valence shell, in the outermost shell. So when it is added to the silicon, the impurity atom, it will form the covalent bond with the 4 surrounding intrinsic atoms, but one bond will be left incomplete because it has only 3 valence shell electron. The 3 electron, they will form the covalent bond with the 3 silicon atom, but the fourth one, that will be left incomplete. And if it is incomplete, meaning the absence of the electron is there, and absence of electron, we are calling it as hole. So we can say that it will give rise to a hole. So basically this trivalent impurity, it is donating hole in the semiconductor system. In that lattice, it is increasing the number of holes. So, and what will happen that Now we will have the large number of holes in the semiconductor in between the semiconductor atom in the intrinsic semiconductor. Now we will have a large number of holes because only 3 atoms they will go to the bonded position, and fourth position will be left vacant, and that will give rise to the hole. Now this hole, it will have a tendency to complete its covalent bond from the neighboring atom. So the electron from the neighboring atom require energy to jump to this vacancy. Now electron from here or here, suppose it can jump to this position because it's a vacant position. So it can jump to this position and can fill this vacancy. So and a very small amount of energy, at room temperature, this amount of energy, it is provided by the thermal energy. So what will happen that this electron can jump to this position to fill this vacancy or to fill this hole. Now, when electron jumps into this vacancy, then what happens is that hole is created in the covalent bond of the surrounding atom from where the electron has jumped. So whenever this electron will jump to this position, then hole will be created here. So this is one thing that after filling the vacancy, a new hole will be generated at some other place. And secondly, after acquiring this electron, this indium, it will have an overall negative charge. So after acquiring an electron, the indium will become the negative ion, and also just like phosphorus, it is also an negative immobile ion as it is bonded from the, it is in the covalent bond. So since indium accept one electron to become negative ion, it is called as a acceptor ion or the acceptor type impurity. Negative ion, this is also immobile as it is tightly held in the crystal by the covalent bond. So overall, we can say that in p-type semiconductors, now it is contributing, this impurity is contributing hole in the semiconductor. So holes will now become the majority carriers and electrons will now become the minority carriers in the p-type semiconductor. So in n-type semiconductors, we have electrons as majority carriers and holes as minority carriers, whereas in p-type semiconductors, holes are the majority carriers and electrons are the minority carriers. Now let's see how the energy band diagram is altered by the addition of this trivalent impurity. So we can see from this energy level diagram that the energy band of the intrinsic semiconductor is modified. So now here we have acceptor impurity level. This is the energy level of the acceptor atom, which is just above the valence bond. So it is there. So energy level of the acceptor impurity is very close to that of the valence band. Now the valence band electron, they can very easily jump to this acceptor energy level as the energy required is very less. So electron at room temperature can easily overcome that gap and can very easily jump to the acceptor energy level. So whenever the electron will jump from the valence to the this acceptor energy level, it will leave behind the hole. So thus at room temperature, we will have a large number of holes which are created inside a p-type semiconductor, and as the holes are the positively charged, so presence of large number of holes, that will make the semiconductor a p-type semiconductor. So now we will have the large number of holes in the valence band. So that is how the energy band diagram is altered by adding the trivalent impurity or the acceptor impurity. Now let's see how the conduction is there in the p-type semiconductor. Again, we have this p-type semiconductor. We have holes now as a majority carrier. So whenever the electric field is applied across a p-type semiconductor, then the current is mainly due to the holes. So holes are shifted from one covalent bond to the another. So positively charged are this, they will be attracted toward the negative terminal of the battery, and that is how the current conduction will be there in the p-type semiconductors. One important thing is that as we are saying that in p-type hole are majority carrier, in n-type the electrons are majority carrier, so it should be noted that P-type and N-type semiconductors, overall they are electrically neutral. The presence of the majority carriers holes or electron in P and N-type, it doesn't mean that they are positively or negatively charged. We just can't say that P-type is overall positively charged because it has large number of holes, or N-type is negatively charged because it has large number of electrons. Overall, they will remain electrically neutral. So that was about the P-type and N-type semiconductor. We have seen how their energy level band diagram, it is getting modified, and how the electrical conductivity is increased by adding the small amount of impurity atoms in the intrinsic semiconductors. Now the last topic is the effect of temperature on the extrinsic semiconductor. Now what will happen in extrinsic semiconductor? Now we have understood the meaning is that if we have added impurity to form the extrinsic semiconductor. Now what will happen if we increase the temperature of the extrinsic semiconductor? The majority carriers are already there. What will happen if in addition to those majority carriers, we are increasing the temperature as well? So what will happen? The additional thermal energy which is there due to the increase in the temperature, that will increase the thermally produced carriers, meaning whenever the temperature is increased, the number of covalent bonds will be broken, and a quite large number of the electrons and holes will be produced. So for example, we are considering the N-type semiconductor. If we are increasing the temperature of the N-type semiconductor, what will be there? Already in N-type we have electrons as majority carriers, but when we increase the temperature of the extrinsic N-type semiconductor, then more and more free electron hole pair will be generated, and at such a certain value of the temperature, the holes will become nearly equal to the number of the electron. So whenever the holes are equal to the electron, then the semiconductor will now act as a intrinsic semiconductor, because we have seen in intrinsic semiconductor, electrons and holes, free electrons and holes, they are produced in pairs. So in that case, in the case of intrinsic semiconductor, electrons and hole number is nearly equal. But in extrinsic, since we are adding impurity, so the number of electrons and holes vary in N-type and P-type semiconductor. Like in N-type semiconductor, electrons number is more. Electrons are the majority carrier. But if we are increasing the temperature, then at a certain temperature in the extrinsic semiconductor, the number of holes which are produced by the thermal generation, that will become equal to that of the electrons again, and the semiconductor will now act as an intrinsic semiconductor with high conductivity. And the value of this temperature in silicon, it is 200 degrees Celsius, and for germanium, this temperature is 85 degrees Celsius. So that is the effect of a temperature on the extrinsic semiconductor, that it will start to act like the intrinsic semiconductor with high conductivity. These are some references. So I hope you have understood. So let's summarize what we have studied in this session. First of all, we have studied the classification of materials on the basis of their conductivity, that is conductors, semiconductors, and insulator. Secondly, how we can differentiate them on the basis of their energy band diagram. Thirdly, the type of semiconductors. We have studied the intrinsic semiconductor, extrinsic semiconductor, its type, and what is the effect of the temperature on the extrinsic semiconductor. So I hope you have understood that this part. These are some references. Thank you.